did this guy yesterday. Let's just look at we'll look at just 3 examples today. How about? Call her good. So on this one, we're supposed to determine the points where the curve has horizontal and vertical tangents. Okay, horizontal tangents, we want to, as we mentioned yesterday, we just want to find the places where the derivative is 0 valued. Vertical tangents, we want to find the places where the derivative is undefined. Okay, so in both cases, though, we need to calculate the derivative, right? So what are we going to get if we implicitly differentiate with respect to x? What are we going to get from our first term? 36y prime. Everybody agree? Okay. So we're getting, whoops, wrong color. 36y prime plus next term, 8x. Last term, 18y prime equals 0. Okay, so then if we solve for y prime, well, we could do one thing. We could simplify by dividing both sides through by what number? 2? Yeah. Okay, good. We could divide each side through by 2. Let's just do that so we get a little smaller coefficients. So then I get 18. I get that. Okay, so now let's solve that for y prime. What's y prime going to equal as a function? Negative 4x. Everybody see that? Because we're moving that guy to the other side, right? So it ends up on top. And what's going to be in the denominator? There you go. Okay, everybody give me thumbs on that. Does that make sense how we got all that stuff? Okay. All right, so there's our derivative function. Now let's go back to the question at hand. So where do we have horizontal tangents? Okay, so for horizontal tangents, that's going to be where our derivative equals 0, right? Okay, where's that going to be? Hold that thought, but that's not the answer to this one. Okay, how come? Right. Okay, but when is a fraction equal to 0? When the top is 0, right? That makes sense? Right? So we know that this fraction is going to equal 0 when the top is 0, okay? So right? Everybody get that? Okay. So x is 0 is the answer to where we have horizontal tangents. Okay, now where would we have vertical tangents? That was yellow. Okay, so vertical tangents. That's going to be where what happens? We've got our derivative. We want our derivative to be undefined. Where is a fraction undefined? I mean, like when we have a vertical line, we said that has an undefined slope. What's going to cause this ratio to be undefined? 0 on the bottom, right? It's the dividing by 0 part, okay? So where is it undefined? Where 18 plus 9y equals 0. That's where it's undefined, right? Where the denominator is 0, which is when y equals -2. Okay? Make sense? Okay, but we might want to know more than that. We want to determine the points. So we found an x value for where we had horizontal tangents. We found a y value for where we had vertical tangents. Let's go back to the horizontal tangents. We need to find an ordered pair. So what am I going to do with that x value to find the y value? Yeah, I got to go back to the original equation, right? We've got this curve that's defined by this equation up here, okay? We know that x is equal to 0, so we would just plug x equals 0 into this equation and collapse it into an equation that only has y's in it, right? Okay, so if we plug that back in, what are we going to get here? I got to make this smaller for just a second so I can see everything. There we go. Okay, so we're going to get, whoops. We're going to get 36y plus 4 times 0 squared plus 9y squared equals 0. Okay, now we've got to solve that equation for y. Okay, so what is that? Well, that just gives us 9y squared plus 36y equals 0. I could divide by 9, right? Or I could factor out a 9y, either way. If I factor out a 9y, I'm just left with 9, or with y plus 4, right? Very good. So what are my solutions to that? Y equals what or what? Okay, so we get y equals 0 or y equals -4. So then what are my ordered pairs? 0, 0 or 0, -4, because we already knew that x was 0, right? That's what we plugged in to solve for y. Make sense? So what does that mean? Rather than just thinking of that in terms of a bunch of algebra steps, why did that happen? What were we thinking? Well, the condition for horizontal tangents, they're always going to occur when x equals 0, right? So if we know that they always occur when x equals 0, we can simplify this equation a little bit, right? So the equation, we know that this equation right here, when we plug 0 in, this equation always holds when x equals 0, but y is still to be determined. Well, we have to solve for y. There are multiple places where y is equal to 0. That's okay though, right? Because we know that for an individual x value, this may not be a function. It's not a function. It's going to violate the vertical line test. Its graph would overlap vertically. So there may be multiple places where this thing has horizontal tangents that line up vertically. They might have the same x value. In this case, they did. Okay, we could graph this thing in a second and see that happening if we wanted. Okay, so there are the places where we have horizontal tangents. What about vertical tangents? Got to do the same thing. We've got to take this function and plug in y equals, what was it, -2? Take this equation, I guess I should say. Okay, so we're plugging that y value in there and there. And we get 36 times negative 2 plus 4x squared plus 9 times negative 2 squared equals 0. Or in other words, negative 72 plus 4x squared plus 36 equals 0. So 4x squared equals negative 36, right? So then doesn't that mean x squared equals 9, so x equals plus or minus 3? So what would my ordered pairs be then for where we end up with vertical tangents? What's the y-coordinate always going to be for every ordered pair? Negative 2. And I have two different x values. Gosh darn it. So don't I end up with the ordered pairs what and what? There you go. 3, negative 2, or negative 3, negative 2. Okay, let's just show that this works. We can look in Desmos and see all this stuff happening. So let's graph the function 36y plus 4x squared plus 9y squared equals 0. And that's what we get. How about that? So where do we get horizontal tangents? Well, yeah, we can see we're going to get horizontal tangents there and there, right? Now, what do we get for our answers? We got horizontal tangents, 0, 0, and 0, negative 4. What do you know? Okay, so it worked out. Where do we get vertical tangents? There, 3, negative 2, and negative 3, negative 2. We found them. Okay, cool. So we can do that. Any questions on that guy? All right, so what about, I'm going to come back to this one. Come back to that one. I want to make sure we get through this one first. I like this one. So this is actually a real application here. So the speed S of blood that is r centimeters, little r centimeters, from the center of an artery is given by this equation. S is equal to C times the quantity capital R squared minus R squared, where C is a constant, then they're going to give us that value. Capital R is the radius of the artery, and S is measured in centimeters per second. So suppose a drug is administered and the artery begins to dilate at a rate of dr dt at a constant distance r. Find the rate at which S changes with respect to t. So can you kind of visualize what they're saying there then? You've got this artery. Like if I drew a picture, we've got this artery. And we've cut through this artery. Right, so there's this artery. And the distance from the center of the artery is measured as little r. Okay, so at some distance little r, they're asking, as the artery dilates, as it expands at that fixed distance, what's going to be the rate at which the speed of the blood changes? Okay, so the units of that, if the units of S are centimeters per second, this is going to be centimeters per second, right? You want to know at what rate is the blood velocity changing at that distance from the center as the artery dilates. Okay, everybody wrap their head around that one? So then what's the constant in this equation? Well, C is a constant. What else is a constant? What else? What are we holding constant here? Little r, yeah. In this application here, we're saying that the distance from the center is fixed. We're going to be measuring or predicting, eventually maybe we'll measure this, we're predicting how fast is the speed of the blood changing at that particular distance from the center. So really it could be any place on this. It's a pretty bad circle, but it could be any place on that circle, right? That's a fixed radius from the center. We want to know at that distance from the center, how fast is the blood speed changing as the artery itself dilates. So capital R is actually variable here. The radius of the artery is changing, okay? So that's the other constant. Okay, so then what are we going to do? We've got this equation that we can start with that relates S and C and both of the R's. What do I have to do to answer this question? What's it want us to find? Here it asks the question, find the rate at which S changes with respect to T. So what am I doing? I'm trying to find S prime, aren't I? So how do I get S prime? What am I differentiating with respect to? T. But I have to differentiate both sides of the equation with respect to T, right? So I'm really doing this. Here's one way of kind of representing this, the derivative with respect to T of everything. So I'm going to implicitly differentiate with respect to T. So what's that going to give me? That's going to give me what? If I differentiate S with respect to T, what do I get? S prime, or ds dt, whatever you want to call it, right? I'm just going to call it, this time I'm going to call it ds dt. That's actually what we're trying to find. Okay, how about on the other side? Well, this is a constant, right? So that's going to stay out front. What's the derivative of r squared with respect to t? 2r, r prime. Okay. And r prime is just dr dt. I'll write it as an actual derivative this time. Minus, what's the derivative of little r squared? 2r dr dt for little r? Okay, but we know an actual value for that. Mm-hmm. You're thinking, right, the big R, but what about what if I differentiate that term? What am I going to get? Well, we said little r is a constant. No. If little r is a constant, then isn't little r squared a constant squared, which is also a constant? What's the derivative of a constant? 0, right? Because we're differentiating a constant. Okay. Okay, so we don't have, that just goes away, right? Question? Okay, yeah, because see, we're not differentiating C by itself, we're differentiating C out in front. Okay, you guys tell me, what's the derivative with respect to x of 3x squared? What's that equal to? 6x, right? Okay, that's a constant, but because it's being multiplied by something, because it's a coefficient, it doesn't go away, it just stays out in front times the derivative of whatever we get when we differentiate. Does that make sense? Okay. Okay, so then there's our equation, right? We wanted to solve for ds dt. Well, we can just plug all that information in that we know now, right? So we end up with ds dt. We'll just call it s prime equals 2c r r prime. And we actually know all that stuff, right? That's equal to 2 times, what's the constant? 1.76 times 10 to the fifth times r is 1.2 times 10 to the negative 2 times r prime, which is 10 to the negative 5. Okay, make sense? And we're just going to get what we get when we plug all that stuff in. We're just going to get some value. You guys are familiar with scientific notation, right? Okay, so then that's just going to give me, well, let's just figure out what is that. So if I plug all that stuff in, I'm just going to get 2 times, I don't think there is like a shortcut way to do scientific notation in Desmos. I don't think, I think I've tried that. It doesn't work. Yeah, it doesn't work. You just get a variable. Yeah. So 1.76 times 10 to the fifth times 1.2 times 10 to the negative 2 times 10 to the negative fifth gives us that. So we get that many watts. We get that many, wasn't it centimeters? What was it measured? Centimeters per second per second. Or per second squared, exactly. Okay. So really what we're measuring there is at what rate is the blood accelerating? And that's it. Not very fast, but it is accelerating a little bit. Okay? Give me thumbs on that. Does that make sense? Okay. Why did I show that to you? Well, because we actually did need implicit differentiation because we're differentiating everything with respect to a different variable, right? Okay, last one, this guy. We'll skip part A. I mean, we would just plug that, would plug pi squared over 2 into the function and just verify that we get that as an outcome if we do that. Okay. Or we plug that in for x and that in for y and just verify that it works. But we don't want to do that. Okay, so skip part A. How do we determine an equation of the line tangent to the curve at a given point? This is a good one to go through after grading the test because I think I'm still not sure this is completely clear what we're doing here. When we're finding the equation of a tangent line, all we're finding is a slope and a point. We already have the point, right? This is the point of tangency right here. Okay, what we need to find is the slope. Slope of the tangent line is just going to be y prime at the point of tangency. That's it, right? So all we have to do is calculate y prime and then plug in this x and y value, and that's going to give us our slope, right? Okay, so this isn't so bad. We need to find y prime. Well, how are we going to approach finding y prime here? How are we going to find y prime from that equation? Say it again. Yeah, we have to implicitly differentiate with respect to x and then solve for y prime. We have to use implicit differentiation because we have multiple y's tangled up in there. Y is not isolated, right? And we don't want to bother to isolate it. So what are we going to get from this first term if I differentiate with respect to x? Yeah, derivative of sine y with respect to x. Well, the derivative of sine hand is cosine hand times y prime. Okay, good. Okay. Plus, how about that one? What's the derivative of 2x with respect to x? 2. Equals, how about that one? There you go. 2y times y prime. And so if we solve for y prime, and you guys are getting pretty good at this. I mean, there's a lot of mental gymnastics to get that. But I'd probably want to pull the y primes over to the right so I can have a positive 2 on top, right? So I've got a 2 on top. What am I going to get on the bottom if I pull this term over to the right side and then factor out a y prime and divide everything else to the denominator? Say it again. Okay, plus 2y, right? Okay, so I'm going to call that 2y minus cosine y. Everybody agree? Okay, so now all we have to do is just plug those values in, and then what do we get? So if we plug those values in, we're going to get 2 over, oh, we don't even have any x's, do we? How about that? The x's all went away. 2 over 2y, that's 2 pi, minus cosine of pi. What's cosine of pi? No, -1, right? How come? Because on the unit circle, it's right there, and we're looking for the x coordinate of that point, right? Which is -1, okay? So we're going to get 2 over 2 pi minus -1 is +1 then, right? So that's our slope. It's a super inconvenient slope, but we just have to plug that in. I mean, it's going to be a mess. I mean, it's going to look terrible, but it's just a bunch of regular old algebra now. So we're going to get y minus pi equals m, which is that whole thing, times the quantity x minus pi squared over 2. That's my line. It's just super inconvenient, but that, by the way, that is, separate that. Almost looks like those are. All I'd have to do is solve for y if I want to, right? But that is the line. If I graph that, that's it. Okay. On the AP test, you could. Yeah. Mm-hmm. Yeah, and I would like you to be able to, but I think typically, like in our books, they'd probably want you to solve it for y, which would be kind of a pain to do. But but you could do it, right? I mean, all you'd have to do is just distribute. This is the slope, so you get that times x. You distribute that to here, and that doesn't help very much, right? I mean, what would it be? We can just see what it would be real quick. So we're just going to get y equals 2 over 2 pi plus 1x minus, if I distribute this, the 2's would cancel, and I'm just going to get pi squared over 2 pi plus 1 plus pi, right? So I guess I would probably, you don't have to make that one big fraction. You could just leave it like this, but you'd probably write it in this form. So this is your slope, and all this stuff would be your y-intercept if you graphed it. Okay, make sense? Looks terrible, but that's it. Okay. Okay, I'm done.